Okay, so in the previous session we had a brief introduction about CFD, what is CFD and why we use CFD. In this session we will get started with the Ansys Fluent by using a simple problem, that is a external flow analysis of a 2D meshed model. Okay, so here we use a airfoil structure for the example. So we have a airfoil structure, and around this airfoil an air passes at a velocity of 20 meter per second from this inlet, and we are interested in the velocity and pressure drop nearby the airfoil structure. Actually it's not a proper airfoil structure, it's look like in the elliptical cross section. Okay, so for example purpose we'll use this structure. Okay, so the first step we need to do here is we need to model the domain. So not on the airfoil structure, so our analysis is only happened on the fluid domain. We can directly model the fluid domain. So the reason we already discussed in our theoretical session, that is in the introduction. So why we need to model the exactly domain, so that is whether it may be a fluid domain or a solid domain. Okay, so the first thing, we'll open the Ansys workbench. So before get into that Fluent model, let us see what are the entities which is available, other Fluent models. So we have so many entities, right? So that is Fluent Flow CFX, Fluent, and Polyflow, and extrusion and blow modeling, like this. And also we have IC engine Fluent also. Okay, so why we use this? So there is no search recommendations to choose this. Okay, this is best, better than this, and this is better than this. So all of them are best in their own way. Okay, so for example, if you are working in an IC engine company, you are only interested in the IC engine analysis, you can go for IC engine Fluent module. So which will have more number of tools which is related to IC engines. Okay, so this CFX and Fluent having the similar GUI, that is graphics user interface. So the both modules which look like same but uses a different kinds of solvers. So some sort of elements will support it in the Fluent and some sort of elements will support it in the CFX. So for most of the aerospace problems, they only prefer Ansys CFX, but in the normal cases we only stick with Ansys Fluent. So in the entire session we only use the Fluent Flow Fluent. Okay, that is Ansys Fluent. Okay, I'll just drag and drop this Ansys Fluent over here. Once it is placed, you may be surprised there is no engineering data at all. Okay, we only have geometry, meshing, setup, solution, and results. And I hope you all are aware of Ansys Workbench. So Ansys Workbench is the prerequisites for Ansys Fluent. So because we can't explain everything about right from the beginning. Okay, so what is meshing, so these kinds will be already covered in our Ansys Workbench sessions. So when I drag and drop any static structural or it may be a random vibration analysis, probably you get an option called engineering data. So by using this engineering data, you can just create material, or you can just add a material from the library source, but you don't get any engineering data at all. So this engineering data is actually coupled with the Fluent model. Okay, so there is a lot of difference between the graphics user interface of Workbench and Fluent itself. Okay, so the process may be a little bit similar, but we have some modifications over here. So we will see one by one what is the difference between the Workbench and Ansys Fluent, for which purpose. So what is the step-by-step procedure? Okay, so while we solve a Ansys Workbench problem, we have a pattern, right? So first we need to define that engineering data. Once it is defined, we need to move on to the next step, that is called geometry creation. Once the geometry is created, we'll move on to the next step, that is boundary condition creation. So the creation of meshing, and then assigning fixed supports and then loads, and we're looking for that post processing, that is results. Okay, what will be the maximum stress and minimum stress. So this is a followed by steps. So likewise Fluent also having some steps. First you need to design the geometry, and then creation of boundary condition, and assigning the initial velocity and pressure, like this. So once we get solve a simple problem, you will know about, okay, so I want to do this thing at the first stage and I will move on to the next step. So follow by, you will get a pattern. Okay, so I will delete this systems, we don't need anymore. So like I said before, it may be CFX or Fluent. The first step you need to do here is the creation of geometry. Either you can import a geometry from some other CAD files, or else you can create by using design modeler or else space climb itself. So I'll use design modeler to create it. So at the beginning stage, we only create a model and try to create meshing and assigning the boundary condition. But in the further classes, we don't yet concentrate on the creation of geometry and meshing, because we detailedly studied about the creation of geometry and meshing in that Ansys workbench session. So that is why we'll directly enter into the Fluent module. So I'll just import a file that is called MSH file. This is kind of mesh file. So what which includes is, it includes the geometry data, so geometry data and meshing data, as well as boundary conditions. Okay, so boundary condition in terms, okay, this edge is inlet and this edge is outlet and this is act as walls. So these kinds of information will available in the MSH files. So when you create geometry and mesh, you just export this file, so that will be saved in the format of MSH. So we we have the hands-on file of MSH. We directly imported that file and do the analysis in that setup, and in the Fluent model. Okay. But if it is the first problem, so obviously we need to start from the beginning. So I'll just double tap on geometry. My design modeler is get started. We need to wait for some times. So once it is created, as per our problem statement, we need to create our domain. So which is having a length of 500 mm and 400 mm height, and we have an elliptical surface like this. So first thing is, you need to change the unit system. So right now the units is set to meters. Go to units and shift over to millimeters. Once the units is changed, just select XY plane, right click and say look at. Go to sketching option, choose rectangle. I'll draw a random rectangle. Okay. Once it is drawn, so before assigning the dimension, I want to apply a constraint called symmetry, because this is exactly lies on the midpoint, midline, right? So from here to here it's 200, here to here it's 200. For that, I'll give the constraint that is symmetry about this axis, so this two lines. Okay, the symmetrical constraint is applied. So once it is applied, go to dimension using general. So it should be around 400, and also I want to mark this dimensions also, that is 500. Okay, this is 500. So once it is created, and also we need to mark this dimension from this point to this point, that is 300. For that I will choose horizontal. So this dimension is 300. Okay. Now we just created this rectangle. So the remaining thing is to create our profile, that is aerofoil structure. So in our case it's a elliptical structure. So just go to the option, you'll find an option to draw an ellipse. Okay, so choose ellipse, click on this point. I'll choose the major axis and minor axis. Once it is selected, you need to give the dimension. So in this diagram they don't give any dimension. I'll use an arbitrary dimension, that is, okay, so in this case it may be 75 and it should be 15. Okay, so we'll get a basic elliptical structure. So once it is created, we need to convert the sketch into a surface. How can I do that? So we have an option to convert this 1D sketch into a 2D. So concept, just choose surface from the sketches option. So once it is selected, either you can choose the sketch from here itself by pressing Ctrl, or else the simplest way is choose the sketch from that tree manager. Okay, so I'll choose the sketch and click on apply. So in this case I don't apply any thickness at all because it's a 2D analysis. We don't need any thickness for this material. Our analysis is only take place on this planar surface. Okay, and say generate. Okay, so our geometries get created. The one thing you need to do here is you need to change the property of the surface. So when I select the surface body in the detailed view, you maybe notice that there is an option to define the properties of the fluid, that is fluid/solid. So right now it's by default it's set to solid, but in our case it's not a solid domain, so we call it as it's a air. It's a air domain. Okay, air in terms of fluid, so not only water or liquid is a fluid. So in terms of Ansys Fluent or CFD, we call it as normal water, fluids, any fluids or air, we call it as a fluid. Okay, so I'll shift to fluid. Laterly we assign that material. So initially we call it as it's not a solid, it's a fluid one. So once everything is defined, so either you can minimize or you can close the design modeler. Now the geometry creation part is completed. I'll move on to the next step, that is meshing. So meshing is very important in CFD. Why? Because probably if you get a very not a good at all mesh, poor quality of mesh in Ansys Workbench, the problem will be easily get solved because of the solver. So in terms of CFD, the CFD uses a special solver. So we know that we already studied about in that theory session. The CFD works under the topic of it uses the method called finite volume method. So it's a volume based method. For that we need to create a very proper mesh. So unless or until you don't get any proper mesh nearby the resultant area, your problem will never converge. Okay, so this CFD solver uses a iterative solver. Okay, iterative solver means, so it solves the problem by iterations, n number of iterations, like 10 iterations, 20 iterations. If you want to, if your problem need to be converged, you should have a well and proper good mesh. Okay, we will clearly explain what is iterative process when we get into that Fluent model. Okay, once the surface body is created, once the body is imported in that meshing environment, the first thing you need to do here is just click on the surface body. So when I click on the surface body, you will have the option to assign the thickness. I don't want to assign the thickness. Just make sure it's set to fluid and check the properties, whether all the values are in the positive. If you get any negative values, probably you'll have any open loops in your geometry. You have to make sure whether it is connected or not in the design modeler itself. Okay, once this step is finished, you will move on to the next step, that is called meshing. Okay, so by default I just create a basic mesh. Just right click and say generate mesh. It will create a base mesh. Probably it's not a good mesh at all. We'll create a fine mesh nearby the curved regions and create a more coarse mesh on the planar surfaces. If you want a well distributed or equal sized mesh, you can just enable the adaptive sizing. Right now it's set to no. I'll choose yes and try to create the mesh again. Okay, it will create a equally spaced mesh. Okay, so there is no much smaller or much bigger mesh. All the mesh elements having the same number of sizes. Okay, so but now it doesn't have any pattern at all. It's in the pave mode. Probably those who are attending the session of 2D meshing that Ansys Workbench, you may understand what is uniform meshing and what is pave meshing. So if you don't have the enough idea, so just try to watch that meshing session. So we'll have a 4 to 5 sessions on meshing. So if you just watch at that, you will get a better understanding about this meshing. Okay, and in the session, in this problem, this is my inlet of the air. Okay, so this wall is acted as a inlet. Okay, so actually the air comes from this side at a velocity of 20 meter per second. So it hits this airfoil structure. Once it hits, it's get out on this side. So this wall is act as outlet. Okay, and this is the boundary ending region. So we call it as a wall. So beyond that limit, there is no fluid at all. So this is our wall. So initially, software doesn't recognize which is inlet and which is wall and which is outlet. So we need to define that. So in this case, this also act as a wall. Okay. So how can we define that? So once we define that, we'll again came back to meshing. How can I create a proper mesh? Okay, we'll see. So first I will define, okay, this is my inlet for this problem. So it's very simple. We already discussed or we seen this option in that workbench itself, like named selection. So we need to create it as a named selection. Okay. So first make sure you are in the edge selector mode. So by just clicking on this option, so now the edge selector mode is turned on. Just choose this edge and right click, and you'll have the option to create a named selection. Just select that. I'll give the name as inlet. Okay, so maybe inlet velocity. Okay, so this term is very important, the word inlet. Why should I actually use this word inlet? It's a kind of keyword. Okay, maybe if you included this word inlet in that Fluent environment, you don't need to assign as a separate one. So otherwise, if you just give any other name apart from that inlet, you need to select that named selection and assign, okay, so this is my inlet and this is my wall and this is my outlet. Okay, you need to define it as a manual. But if you included that keyword, software will automatically recognize, okay, so this edges act as an inlet and this edges act as an outlet. But only if you included that keyword inlet, outlet and wall, it's a kind of keywords. Okay, you will understand by the following problems. So I'll choose inlet velocity and say click on OK. So now it is selected, created. And the next thing is, I just choose this and right click and say create named selection. I'll give the name it as a outlet. I don't want to give any velocity or pressure. It may be a pressure outlet or a velocity outlet. I'll just name it as a outlet. Okay, and this four things will act as a wall. Right click and say create named selection. I'll just simply as wall. Okay, fine. So just make sure all the edges are correctly assigned. So this is inlet and this is outlet and this is wall condition. Okay, so once it is created, we'll create a proper mesh. So actually I am only interested on this region, okay. So what happened nearby the airfoil structure? Okay, so how the velocity and the pressure is dropped or increased nearby the airfoil structure. So that is my interest. So for that I need to create a proper mesh nearby this wall region. We have a n number of meshing option. I'll use one factor, that is inflation. What inflation will do? So the inflation will do which creates a proper mesh nearby that edges. Okay, so I'll choose inflation. It asks you to select the geometry. So in this case it's my geometry, phase number 1, and it asks you to select the boundary. So this is my boundary region and click on apply. And how many layers you need? So by default it has in 2 layers and having the growth rate of 1.2 and transitional ratio. And hope you know about this like growth rate and this transitional ratio. We already discussed about in our workbench session. So like growth rate means the transition between the fine element to the coarse element. So we'll have a small element and probably you'll have a big element. So what will be the growth rate? Whether it may be a gradual growth rate or it may be a sudden growth rate. So it depends upon the growth rate. Okay, so that is what we give it as a growth rate. Okay, so I don't want to change anything. I just give the inflation factor and right click and say generate mesh. Let's see what will be the mesh, how it's actually created. Okay, so right now I'll give it 2 layers. It creates a 2 sets of layers nearby the wall region. Okay, But if you want more number of walls, I mean more number of layers, you can click on inflation factor. I'll increase to 5 and right click and say generate mesh. Okay. So I'll have a more number of layers, like 5 layers, 1, 2, 3 and 4 and 5. Okay. So this is more than fine. So still if you want a more refined mesh on the outer surface, you can give a sizing factor also, but in this case I don't want to give that at all. I'll use the standard sizing, or else you can change from here itself also, but I'm not interested in that. I'll use the standard mesh at all. So if the problem is not converged, we'll again get back to that meshing environment, we'll change the mesh sizing and try to solve the problem again. Okay, I'll close the meshing. So once the meshing environment is get closed, you'll get a thunder symbol on mesh. So that means everything is assigned, but the data created will not transfer to that Fluent environment. If you want to transfer the data, just right click on the mesh and click on update. So this update process will do which transfer the entire meshing data to the Fluent module. Okay, so it will take some time, we have to wait for it. Okay, so once the data is completed, just double tap on the setup. Now the Fluent environment is get started. So this is the welcome screen of the Fluent module. So currently we are using Ansys 2020 R2 version. So it's a cracked version, but if you are using students version, probably you'll get a lot of restrictions. So that is why I'm using cracked one. So here you have a varieties of options. But if you are running a server based system, having one or more systems, you can use a parallel local machine to get you can compute the problem more faster. So you can set the processor in the series mode. Simultaneously the problem will solved by a series of 3 to 4 processors. Okay, but we only working on a single machine, we don't yet use these options. And there is another option that is called double precision. So that means it may increases. So if you just enable this option, your problem convergence level will be increases. Okay, so the more number of probability your problem will converge. Okay, and also the solving time will little bit higher than the normal cases, but usually we enable this option for a complicated problem. For this problem, maybe you can enable or disable this option. I will just enable this. So there is an option to shift over from 2D to 3D. By default, you only create a 2D structure. So there is no other way to shift over to 3D. So that is why this option is hidden. Once this option is selected, just click on start. The Fluent will get started within a minute. Okay, now the Fluent environment is get loaded. So I will quickly explain the graphics user interface in the Fluent module. It's very simple, easy to understand. So like always, the top bars we call it as a quick access toolbar. So we have refresh button and update button, everything we have. So if you want to use that, you can. And also you have a file, domain, physics and user defined and solution results, view, parallel designs options. So this is a ribbon bar. So accordingly, if you want a file management tools, you can shift over to files, and domain related tools, shift on domain, physics, user defined. We will laterly discuss about this option in our upcoming sessions. So for now, I just minimize this option. The main thing is outline view. This is our outline view and this is our task page. Okay, what it will do is, in Ansys workbench itself, we clearly studied about the process. That is, we have three types of process. One is pre-processing, and solving, and post-processing. Okay, so what the pre-processing will do is the creation of model and boundary conditions applies and meshing. These kinds we call it as a pre-processing. Once this part is completed, the second part, the solving part, is the problem will get solved by the solvers, that is numerical solvers. Once the problem is solved, we'll get a numerical data. So we can't directly interpret with that data, right? So obviously we need a certain environment to decode that particular data and view the results in terms of contours, colored images, or else graphical formats, right? So that is why we call it as a what is that, post processing environment. So here also we have a three categories. One is setup and solution and results. So the setup is for pre-processing state, and solving is for the solution is for the solving part, and result is for the post-processing environment. So this is the three major thing. Let's see one by one. What will be the task, or what is the use of the task page is, whenever any entities, I'll click on this model, like if I choose general, so the general options will be shown over here. So if I double tap on the model options will be shown in the task page. Okay, you can easily access or change by from the task page itself. And so this is what task page will do. And you also have an option that is called a console. So the console is nothing but it shows the information which is related to your problem. So maybe some boundary conditions, what are the materials it is imported, and the mesh data. And if you get solve this problem, you may be sometimes you may miss some boundary condition or cell zone condition, or else you may miss some materials to add. So that information will be noted down here. So any errors you can get from here itself. Okay, or else sometimes you can give command itself also, like a scripting. Okay, so when I click on check, so I'll get a checking data. So that is also be visible in the console. Okay. So the first thing you need to do when you get enter into that Fluent environment is to check the everything is correctly assigned or not, the volume statistics and phase area statistics, everything. Okay. So by clicking on check options, and like always, so this is your graphics area. You can zoom in or zoom out the model. So I already said that. So when you use this keyword, that is inlet or outlet like this and wall condition, software, the Fluent environment will always recognize that keyword. So I'll use that keyword. So that is why it shows the arrow. This is for inlet and this is for outlet, and wall is assigned in the brown color. Okay, so usually that is not shown. Fine. So this is our graphics area to view the model in 3D and as well as 2D. Okay, and we'll move on to this options. We have so many options, but in the particular one session we can't explain everything. I will show you a overall thing. So how to solve the problem. We will clearly explain what is the scale means and check report quality and display units in that upcoming session. So we have a series of sessions, right? I'll explain in that session. Okay, for now I'll choose pressure based because I'm working on a fluid, that is air. So air is a compressible flow. So if it is a compressible flow, we can go for a pressure based model. So if it is a liquid, so there is a flow in a piped session, a liquid is flowed in a piped session, we can't compress that liquid. Okay, so for that we can go we will move on to that density based one. At the most of the stage, like 80% of the problem will only based upon the pressure based one, only of 20 or 15% will use the density based models. Okay, and in this case I will choose absolute and steady state. So absolute means there is no changes with respect to time, the velocity is a constant one here, and this problem is a steady state one, it's not a transient one. So when the data and the boundary conditions changes the values with respect to time, I'll move on to the transient cases. And also it's a planar analysis, it doesn't have any axisymmetry condition, I'll choose planar also. So in this case I don't add any gravity at all. So if you want to add, you can just enable this option, you can define the gravity factor at all. Okay, so once this step is finished, I'll just move on to the next step, that is model. So this model is very important, and hope you heard about this term. We already discussed about these things in that introduction of CFD. So in the introduction of CFD, we talk about the CFD solvers. The CFD solvers will basically solves the conservation of mass equation and energy equation and species equation like that. So if you enable that equations, the equation size will be much more bigger, and if you disable that diffusion factor, what is that, convection factors like that, the equation become much more smaller. Okay, so how can I enable that options? So you can enable that options from the models. Okay, so you'll have so many options, multi-phase, energy, viscous, radiation, and heat exchangers like that. You can enable that problem. So if your problem really need that case, you can just enable and define that factors. Okay, so but this case we don't need to use any multi-phase, or there is no temperature related thing, so that is why I just disable that factor like energy equation. So I only choose viscous condition. So basically this viscous condition, why we use is to define that flow of the liquid, I mean flow of the fluid. So there is two types of flows, one is laminar flow and turbulent flow. So other than that, like if your flow is a laminar one, so you know that, so laminar is a kind like this, so the liquid is flowed in an equal manner, so there is no disturbance at all, the liquid is flow like this. So but maybe the blood is also flows in the laminar condition, it's a kind of laminar flow, but most of the cases it may not in the laminar condition. What will be the turbulence? So the turbulent flow like this, so the liquid having a turbulence like a spinning waves, you may have the turbulence like this, the flow may be. Okay, so apart from the laminar, all of the things like K epsilon or K omega and Reynolds stress, these conditions we assumed as a laminar, I mean turbulent flow. Okay, but this is a laminar condition, we assume this flow is a laminar, so I'll choose laminar. So to solve the laminar problem is very simple, the problem is easily get converged. So other than that, if you go for K epsilon or K omega like a turbulent flow, it's very difficult to get the convergence factor. In that upcoming sessions we will looking for that K epsilon, K omega in Spartler equations also we have a problem. Okay, I'll choose laminar and say click on OK. So once it is settled, we need to define the material, but fortunately we'll have two options. So when I double tap on the material, we'll have fluid and solid, so we don't need to have any solids at all. In fluid itself also we uses the standard material, that is air. So that is why we don't need to create any material at all. Okay, this material looks like our engineering data in that workbench session. So we can add n number of materials here itself, because to define the material in Fluent itself we have two things, one is material and another one is normal cell zone conditions. Okay, why we need this cell zone condition means we have so many surfaces, right? So in this case we only have one surface, but in a complicated state we'll have so many surfaces and so many domains. We need to assign, okay, which surface is which liquid. Okay, this surface is air and this surface is act as a nitrogen or carbon dioxide or NO2, where some whatever it is. Okay, we need to assign that, right? In materials you can add n number of materials like air, carbon dioxide, or else in solid itself magnesium, copper. So by using cell zone condition you can assign this material to a particular surfaces. Okay, so by default air is added, I don't want to add any other materials, I just leave as it is. I'll move on to the next step, that is cell zone condition. When I double tap on the cell zone condition, you'll have a fluid domain, only we created a fluid domain. So I'll just create, select the surface body and click on edit, make sure the type is set to fluid and say edit. So the surface body material name is selected as a air. Okay, so if you want to choose, if you add any other materials in the material library, you'll get all the materials in that pop-up. So you can choose what are the material you need and click on apply, so that material will be applied and say close. So other than that we have a boundary conditions. So in that boundary condition we have inlet velocity, outlet and wall. So by using this you have to define, okay, the inlet velocity of the air and outlet condition, everything you have to define from here itself, that is boundary condition. I'll start from the inlet velocity. Like I said before, if you use the key term, that is inlet, software will always assign the type as an inlet velocity. So if you give any other name, you have to manually choose from here itself. You have so many conditions like axis, exhaust fan and intake fan, like this. From this type you have to choose which one you want. Okay, by default velocity inlet is selected. When I choose this, and another pop-up will be created. Okay, so in this condition we need to apply the velocity. So I'll have the option to assign the velocity in meter per second, but I need to specify the method. So right now magnitude normal boundary is chosen. Shift over to components. So this is x, so it's x and it's y. So the velocity is acted in the x direction, in positive x. I'll give the factor that is 20 meter per second and say apply and click on close. Now the inlet velocity conditions will be defined, and move on to the next thing, that is outlet. So outlet, right now it's set to pressure outlet, but I don't want to give any pressures at all. I'll give complete outflow. So whatever the inlet velocity which comes inside the boundary, so we'll move on, we'll get out from that outlet. I'll give the factor of 1. So if you give the 1, the 100% velocity whatever it is comes inside will be move on the outside. Okay, there is no restriction at all. So if I give the factor of 0.5, only the 50% of the liquid will be outed on the outlet. Okay, so maybe if the velocity of 5 mm will be comes on this end, so only a 2.5 velocity will be comes out around this, crosses this boundary. So that is what it means. So I'll give 1 factor and say close, and just select this wall condition and assume that the type to be wall, make sure, and say click on edit. The wall condition is get open. So maybe whether it is a stationary wall or else if it is a moving wall. So in my case it's a stationary wall, and if you want to specify the shear, you can specify the shear. So right now we don't have any shear at all. I'll just leave as it is and click on apply and say close. Once the boundary condition is get created, I'll directly move on to that methods. Okay, so apart from that we have so many steps, but we will discuss about these steps in our upcoming session. So right now I'll use the standard things. I don't want to change anything at all. Just click on that initialization part. Make sure it is in the hybrid initialization. I'll just click on initialize because it's an iterative problem. So what is iterative? So iterative means in some cases in that workbench itself we have equations like ax plus by is equal to 0. Okay, so if you know the value of anything, like we assume that x and y is 1 comma 1, x and y is. So if you know the value of b, you can find the value of what is that? If you know the value of a, you can find the value of b easily. Okay, by just substituting the x and y values, and you'll have this equation solving value also 0. You can easily find the b. But in such cases, you don't know actually the value of a and b. Software try to assume that value of a, that is a dash x plus b dash y, and is equal to 0. If the equation is satisfied, we try to assume or change the value of x and y, and again apply the same factor of a dash, and try to change the another value of x and y, because if you change this value, still this equation want to be satisfied, and same using the same value of b dash and use the same value of y, and try to solve this problem. If it is solved, the problem will be converged. Otherwise the process will be repetitively happened until the problem will converge. So these two values will be same as like, that is why we call it as a iterative problem. So still if you get if you want a better understanding in what is iterative problem, so just type on Google, so what is iterative problem solution method, we assume that values initially and try to solve the problem and get the values actually. So this is the initial value to get start the problem, like a 10 iteration. By using this value, the problem will get started. I'll move on to the run calculation part. I'll give a basic iteration factor of around 300 iteration. So there is no search recommendations. So sir, how can I assume that sir iteration factor? Okay, you can give any iteration factor like 100 or 200 or 300 or 400 mostly. So the problem convergence will greatly depends upon the quality of the meshes and the reliable boundary condition factors. Okay, so what is that reliable or appropriate boundary condition? In some cases, you may give a boundary conditions which is beyond the limit. Okay, so we'll have a car structure like this. Suppose you want to find a air drag analysis. So you'll assign the velocity. This car moves around in a 80 km per hour. It's a reliable one. So 80 km or 40 km. There will be some range, right? So if you give the range very minimum, so if you say this car moves in the velocity of 0.085 km per hour, so it is not reliable. And if you have a more value like 8000 km per hour, it's not a reliable one. In such cases, the problem will not get converged. And also if you get a very poor quality of mesh, the problem will never converge. So this is the reason problem may not be converged, right? So I just give a 300 iteration for this problem. Let's check whether the problem is converged or not. Okay, I'll click on calculate. Now the problem is get started. Okay, so now the problem gets completed. So even though if the problem is not converged, the calculation is actually completed because the 300 iterations is actually completed. Okay, so there might be a lot of reasons why the problem is not converged. So how can I make sure that okay sir, my problem is converged or not? So all the values you should be here, right? So this should be below the difference between the two numbers is actually a 10 to the power of minus 6. It's a very minimum thing, like a 0.00. The difference will be allowed. So when the two previous values is equal, the problem is automatically converged. So what I simply do is I just change the mesh configuration. Probably it's a kind of, if you get a poor quality of mesh, you maybe end up with the inconvergence factors. So get started the meshing environment, right click and say insert sizing, choose this option and click on. I'll use a sizing factor of 20 or else 10, right click and generate mesh. Okay, so I'll get a proper mesh like this. I just close and try to update this mesh. So once the mesh is updated, double tap on setup. Okay, now the Fluent environment is get opened. So you'll have the option to refresh the input. So it asks you to change the update the changes for the same inputs. Yes, I want to. Now the boundary conditions is get updated and meshing is also updated. So if you want to view the model, so it will take some time to get loaded. Okay, now the mesh configuration is get changed. And again I will click on calculate for the same boundary condition. I don't change anything at all, just click on calculate. So it asks you to proceed from the same initialization. Okay, so I'll move on to the initialization part and click on again initialize. You'll get a 10 values and go to the calculation and say click on calculate. Okay, see, now the problem is get converged at 57. Okay, so like I said before, the convergence factors is greatly depends upon the quality of the mesh. So in the previous case, the mesh is in a pave mode. Okay, it's not in a uniform manner. Okay, but in this case you will see. So when I double tap on this model, okay, I'll say I want to display all the things. Okay, you will clearly view this. See the mesh pattern. So it's in a well and good manner. Okay, so that is why the problem is actually converged. So even though I give the factor of, iteration factor of 300, anyways it converged in the 54. In some cases it may be converged, in some cases it may not be converged. So there may be a lot of factors which affecting the convergence. Okay, so once the problem is converged, you can just close the Fluent model. We'll move on to the post processing environment to view the results. Okay, so now the problem is everything, we have a green color tick, and double tap on the results. Okay, so this is our CFD post environment. I'll explain the graphics user interface in that upcoming session. For now, as per our problem statement, we only interested on the velocity and pressure drop nearby that wall region. So to get the result, you will have the option to create a contours. Just select the contour option. I'll name it as a velocity 1. Velocity 1. So once it is named, click on OK. In the detailed view option, you will have a geometry, labeled, render, view. So I want to view the velocity change in the location of symmetry 1. So that is the planar surface, and the variable is obviously velocity. Either you can choose global or local, it may shows the same results. It's not a great thing. So I will increase the contour range. Okay, so first I'll just leave to 11 and click on apply. You'll get a velocity drop result. So you'll have a maximum velocity at this region. Okay, so suppose you only have 11 colors, because I give a contour colors for a 11 one. 1, 2, 3, you'll get 11 gradients. So if you want a more smooth contours, you can increase the range. So now I give it factor of 200 and say click on apply. I'll have a smooth factor. Okay, I have a maximum velocity at this region. So suppose you don't want any scientific notation at all, you can change from here itself. Click on edit and go to appearance and change the factor to scientific to fixed one and say apply. You'll get a whole number value. Okay, it start from that minimum velocity is 3.79 meter per second, and the maximum velocity is 24.263 at the range of this red color having a maximum velocity. Okay, I am interested to view the pressure result. How can I view that? Okay, so I just disable this velocity and move on to the contours again. I'll name it as a pressure 1 and say OK. So the region is symmetry 1. I want to view the pressure. You can give the factor as 200 and click on apply. Now you get the pressure result. Okay, you know that the velocity and pressure is vice versa. Where there is a minimum pressure, you will have a maximum velocity, but if there is a maximum velocity, you will get a minimum pressure. So at this region you will get a minimum pressure, and here you will have a maximum pressure. Okay, so you can just zoom in or zoom out the region you need. So apart from that, we have so many options to view the results. So if you want to view the pressure result and velocity result at a time, you can choose a 2-layer. So in that view 2, I want to view the velocity. Okay, so in this case you will have a velocity, in this case you will have a pressure difference. Okay, so that is all for this session. So what we actually seen in this session is a overall view for the CFD analysis and how can I solve a basic CFD problem by using Ansys Fluent. Okay, so in our upcoming session we will clearly see what are the different kinds of analysis, what will be the meaning of these models. Like we have so many models, like other than that K epsilon and Reynolds number. We'll clearly explain in that upcoming session. Okay, and hope you all enjoyed this session, and we'll meet on our next session. Okay.